Hello, we are discussing bistable compliant mechanisms or the phenomenon of bistability in elastic systems. We had two lectures. In the first lecture, we talked about what bistability actually means in an elastic system. In the second lecture, we discussed one class of bistable elastic systems, which is arches, and we discussed an analysis method that lets us analyze the bistable phenomenon, and we said that that same analysis method can also be used for synthesis. We will discuss a few applications today, so that we understand how bistable arches can be used in real applications. Okay. So, let us look at this application of bistable arches in compliant mechanisms. The basis for what we are going to talk about is captured in this bistable tin lid. So, what we see here is a tin, little tin, that is a small one, which has it is all rusted and so forth, still works. This lid of the tin, this is the tin lid, the top surface, and there are some flaps on the sides. There are flaps like this on the sides, and there are slit here, so that there is a little thing here in between, the little slit, and this has a very interesting bistable behavior. It is a metallic tin, but it has very interesting behavior, and its diameter is 47 millimeters, thickness is 0.38 millimeters, 380 microns, flap height is 5 millimeters, the height of this is about 5 millimeters, it is made of spring steel. Okay. So, here is a sketch of this device. It is a click clack tin lid. When you press on it, it makes that click sound, and you can take out the lid. Lid is very tight when it is on the bottom thing here. This is the lid, this is the tin. When you press on it, it becomes loose and you can take out the lid, and then when you want to close it, you have to press on the sides. You have to press on the sides of the thing, and it makes the clack sound. Let us hear it to see what this click clack sound is. What I have shown you is this tin lid here. So, there is a tin and there is a lid here, and it is very tight. So, you cannot open it, you can turn it like this, but you cannot open. If you have to use a lot of force if you want to open it this way, but it will open if you just press that way. That is a click sound, you heard it. Now, it easily comes off, right, it just comes off. Now, if you want to put it back, before that let us see the bistability here. This is the tin lid, circular, and there are flaps on these sides here, and it is underside, and if you look from the side, there is a little curvature down here like this. So, you can do this, click and then clack, click, clack. So, you can do that, but then when you put it on the tin, then you cannot go underneath to push it like that. So, what do? That is why there is a nice design feature here with these flaps on the side, which are slit. You can see the flaps on the side, right. So, if I put it and then press it on the flaps from the side, it makes that clack sound. Now, it is tight, it does not come. So, I have to really apply a lot of force to take it out, but I cannot put it back also that easily because these flaps are there. So, this click clack is the thing here. This such a thing we call it bistable bimodal or bimodal bistable device, because it can be switched back and forth like this, and it can also switch back and forth like this. So, this way and then return in another way. So, this click clack tin lid is what we are going to analyze or also use it in applications. First, let us look at the energy and force curves in this bimodal bistability. So, what is shown here is an energy curve. Again, energy here is potential energy. So, we have potential energy, and there is a rotation angle given, that is the angle if you were to look at a one dimensional model, which we will discuss, but the idea is that it has potential energy which is like this. So, there is one stable position here, another stable position there, there is an unstable position, this is stable, stable and unstable. Okay. And the dashed curve is the force curve, that is a derivative potential energy, that is the force curve. It is 0 here and 0 here again, it is also 0 in between, but that is the unstable point. Okay. So, the force is shown on the right hand side with this dashed curve. It is a bistable device. It is also bimodal because when we have the actuation, what we can call port 1 actuation, where we press it like it is shown here, and the port 2 actuation where press it on the sides. So, it has two ways that you can actuate, that is why we call it bimodal. There are two modes of actuating this tin lid, one this way and the other second way, right. You can go back and forth between state 1 and state 2. So, if you look at the energy graph for this, we are showing the potential energy curve in this line, solid line, and then dotted line is the potential energy when there is port 1 actuation. The first one, in fact, we need not call it potential energy, this is simply the strain energy of the elastic body of the tin lid. Strain energy plus work potential become the potential energy. So, there is no force, that is excluding the force, that is strain energy itself that we have. Then we have port 1 actuation, potential energy, and then port 2 actuation, the other potential energy. This is strain energy, this is potential energy with port 1 clicking sound and then P2 clacking sound. Okay. So, how does it operate? When strain energy is the way it is, imagine that there is a ball here, and the moment the energy landscape, this is all the energy that we are plotting, energy landscape switches from strain energy to PE1, the ball starts rolling until the curve remains is black one, the ball will be where it is. The moment you apply potential energy 1 landscape, that is you apply port 1 force, it becomes like this, and the ball from there would roll and reach that point. Then you remove the force, it comes back to where it should be, that is a second stable state. This is stable state 1, this is state 2, it comes there. Now, you want to switch it back, of course, you can come back in this way and then go there, that is energy landscape moves again from SE to PE1, then it will retrace its path, but what we do here is change it to PE2, then from there it would take that path, because that is the minimum now, comes back here, and then when you remove second port actuation, it will come back there. So, going and coming back are different here, that is the bimodal bistability that we see in this unique tin lid. So, depicting in using a figure, you have a point P1 in energy state 1 goes to P1 in energy state 2, a point, and when it comes back it will take a different path, because you are applying force elsewhere at a different point, and that P2 in that energy state 2 will come back to P2 in energy state 1. So, going back and forth, if this is our port 1 actuation, then these are our port 2 actuations. If we take a point, it will take one path going that way, and then when it is here, okay, let us say that point when it goes there, let us say that is here, then it will take a different path to go back to this. So, from here it will take a slightly different path to go back, it will come like this, go like that. So, that is what we have. So, that is what is being shown here. The paths between the two states are different. When it goes from state 1 to state 2, it goes along one path, and then coming back it takes another path because the actuation force itself is different. And this double cosine curve that we had discussed in the last lecture, the reason that it is there is to prevent the asymmetric mode that exists in this one. So, double cosine curve is only you apply the force here and then you put it back here when it goes to other side, that is only a single port bistable mechanism. You can apply force elsewhere, but pretty much they will all be similar, but not like this bimodal one. If you want bimodal one, we can use pin joints here. So, we have pin joints there, and then you can apply force that way, that is a port 1 actuation, or you can also apply force on here or a torque. In this case, if you move it up like this, it will try to switch back to the other position. Okay. That will be the port 2 actuation, as we will see the movie here. So, if I run this, you will see that both simulation in this figure, okay, let us put that there, yeah, simulation in the figure over here, and you can see as the force is applied how it is going to switch to other position. We can see it here also. So, we have it there, when you switch it, it goes to the other state, pretty much looks like the thing as a simulation where you are applying force and it will switch to the other position. So, let us play that again to see this simulation over here, finite element simulation, it comes. So, you have the force applied, it goes to other state, you can also apply the torque if you want, both ways it would work. Okay. This is the 2-dimensional version of the tin lid I showed. Now, you see when you press on the sides, it goes back again. So, let us play it from here. So, it is in this state, when you press the there, it will switch to the other state. So, I have these things here, so you can actually see it in the real one. So, let us put one of these over here, what we saw in the simulations there. This is an arch which has the pin joints, and there are also flaps, just like the thing has on the sides the flaps. We take one section of it. Okay. It is a 2D version of that. If I call it a shell, this is this. Now, I apply a force in the middle. This is one stable state where we are. Now, when I apply a force, it will go to the other state, that is the second state. It is stable, no external force, that is a definition of bistability, that is it has two stable states without external force acting on it. Now, when I apply a force back, it of course comes back, you can see how it actually snaps, because this is as fabricated load free or stress free state. Now, when I do this, now it is under stress, that is why when you apply force it just snaps back. When something under stress, it won't relieve its stress. So, I can do this. I can also do this by applying torque on this flap, that is I can rotate this flap like this flap like this. So, I can push like this and also do that, right. I can either do this or I can do the other way. There is a pin joint here that I will just put it in. There is no preload here. I can just do this, apply the force, it stays in another stable state, move it back. There are different curves, that different arches we talked about. If you take the buckling mode shape of a straight beam, so here is actually the combination of the first and third thing, looks more like a bow. So, this particular one, this is one stable state, apply a force, it goes to the other stable state. Okay. Apply a force back again, it comes back, right. Now, if it is here, I can also apply the torque here and it switches. So, the force required for going like this, right. So, there is some force I need to apply, the force required on the sides is very little, Okay. That is something we will exploit when we consider an application. So, there are a number of shapes that you can take. Here is another shape which looks slightly asymmetric, that also is asymmetric shape, and that also goes bistable, right. Again flaps are there to switch it. So, we have two modes of actuation over here, as opposed to what we consider this the switch, the electrical switch that we have, tuck that we have all the switch boards, that has a nice little mechanism, interesting, simple, but not that much in terms of analyzing. It is very simple lever that it has that noise you can hear. Yeah. So, that is single mode bistable mechanism, whereas the ones we are thinking are the bistable mode. Okay. So, if you look at the two stable states in this particular case, you would see that it is actually deformed, because if I take this curve here from here to there, right, let me use a different color that is more visible. If I take the curve from there to here, if I simply rotate, I get this. Okay. But what is happening in the other stable state is it is deformed. That means that in the second state, this deformed one, this is stressed. So, there is stress in it, whereas the original one as fabricated is stress free state. Okay. That is how this bistable thing works. So, when you apply, when it is other state, when I just apply forces like that, it is going to switch back to the other state. From here it will go back there. How do you model that? We had considered a single degree of freedom model earlier. We can also consider 2 degree of freedom model. So, it basically says that if you have a spring like it is shown in state 1, when it goes to the state 2, in between it goes through a maximum stress or maximum strain state, and that gives the bistability. We can capture that over here with a torsion spring there and a translational spring here, and we can have port 1 actuation and a port 2 actuation, a single degree of freedom model that we are considering once again now. So, we can write the strain energy for this. Once we write what is the torsion spring, what is the translational spring constants are, and sketch this energy landscape. We can actually do everything using trigonometry, the delta, that is how much this is moving, and the theta, how much it is rotating over here. Then we can write this for various forces. We can see how the energy landscape changes. The original one that we have, this one over there, and then how for different values the energy landscape changes and where the other minimum would lie. We can make all of these things. Okay. Likewise, when I apply port 2, which is the torque over at this joint, okay, that also original one looks in particular way, and depending on the force for the port 2, we are applying torque by applying a little force on the flap. This is the flap here, we apply some force there, that creates a torque at that thing. For various values, again we see how the thing changes, and between the, when both of them are there, we said that to go from here to there, it comes along one path, going back it takes another path, as it is emphasized over here. We did high speed video of these things which I demonstrated. If you notice here, it takes one path and then takes another path to go back, and that is the bimodal feature of this one. We used biaxial system so that we can hold it, we can apply force this way on the arch as well as this way on the flaps. Okay. So, with that when we record, it indeed that take a different path. When I play it on the thing, you would see that it goes very fast. So, you cannot be sure that it is taking, simulation show that takes a different path. Here experiment also with high speed video, we can see that it takes a different path. So, with this bimodal bistable compliant mechanism, since our lab we work on macro, meso and micro, we have one application for both. This sit to stand easy chair is a macro application, and then this is a micro application RF MEMS switch, and then we have miniature circuit breaker, that is the meso scale one. So, we have 3 applications that are being pursued with one concept. We discuss the chair now and in a case study later, and also RF MEMS switch we will discuss now, and then the bistable circuit breaker that is being done with a company. So, I have intentionally blurred it all so that we do not reveal all the details, but essentially it uses this bimodal bistability of having this force deflection behavior and this two minimum energy states. Tuning the stiffness and stability at different length scales is what being done here for the chair, for the micro switch as well as the miniature circuit breaker or the meso scale one. Okay. In all cases the paths are different, and that makes it an interesting problem. So, let us look at this easy chair based on this bistable device. We said that the click clack tinlet force in one direction is much more than the force in the other direction. So, for the easy chair like this, if somebody sits in the chair, the weight of the person is the force, that is port 1 actuation. When they want to, they go to the other stable state and comfortable while sitting. When they want to get up, they will press on the handles, that is a port 2 actuations, much like pressing on the flaps of the tinlet, little force with enough leverage that will gently push them. It will not make them fly like a projectile, it will gently push them. That is this bimodal bistable chair, easy chair. So, the idea, this is the port 1 actuation and this is the port 2 actuation as it is mentioned. Okay, that is what you want to do here. So, chair up and down, there are 2 states, and static balancing. So, that energy state if we do, if it is complete static balance, that is a good thing. We will be talking about static balancing in the next set of lectures. And bistable is like this, we have up position, down position, in between we have to go over a hill to settle down in a minimum like in state 1 and state 2. So, here is a model of that of the device. So, it is actually several bistable things are over here on the side, and they can go from that state to this state to apply. If somebody sits there, they come back and here, and they are stable over there, and of course, no force, equipment is not there, it is stable. It is done with these springs, and we will discuss static balancing in the next set of lectures. Okay. And here these springs are used in a pre-stressed manner, that we will discuss later how to pre-stress them, so that there will be energy stored in them to begin with, and that energy gets released when you want to switch back to the other state. And the weight of the person, that energy will be stored in the springs, which will itself help the person to rise from the chair. And very small force needs to be applied on the handles, much like our tinlet. Force required for port 2 activation is smaller than the force required in the port 1 actuation. And that is how this chair was designed. Now, we will be discussing that chair in a case study in great detail in a later lecture. Right now, let us look at this 2 terminal bistable RF MEMS switch. MEMS stands for micro electromechanical systems, RF stands for radio frequency switch. In switching antenna arrays and so forth, it 2 terminal meaning there will be only 2 electrical terminals, which is appreciated by power electronic designers when they use power supply. Then if it is 2 terminals, it is much better for any device that they have. It is actually 2 terminal. There is a ground, another part ground, there is a voltage applied, in 3 different places. Okay, but there is only one wire that goes with all of these things. Between this and this we have common ground, and there is another one which is like a floating thing here, or it could even be ground. Okay. So, what will happen is when you supply force, it is a V beam electrothermal actuator, it applies the force, it switches to from one position to another position, and then it touches and it contacts with the RF line and makes or breaks the switch, and you apply again, it will try to switch back. It is also kind of a bimodal bistable device. Design constraints for this problem: it has to fit in a 5 by 5 mm die, contact force should be at least 100 micronewtons, it has to withstand 100 degrees centigrade, 110 degrees centigrade, resistivity some value is given, it should be a 2 terminal device. And this is the design here. So, you apply force like this by applying between ground and the voltage actuation point. So, that will move from there to here to switch, and then it will push this here, okay, and then it will push back to the other state. I think it is best explained with these two diagrams. When you do this, it will switch back, and then when you do it again, it will switch back to the original state from there and here, and similarly this is shown what happens with various actuations given, how it switches from one to the other state, on state over here to off state over here. Okay, there is a small variant where the force is applied here for port 2, this is the port 1. If you do that between voltage and ground, if you do this and this, both will be there. In one case when it is here, it switches to the other state, and the other case switches to the back to the first state. So, we can watch this movie. So, now this actuation is applied and it is moving down and down, it will go to the other state. Now, when you pull it back, it comes back to the same state. Okay. Let us play this again. Let us play this. Okay. Yeah, actuation, electrothermal actuation, when it is pulled that way, switches from there to here, and then when you pull this way, switches back to the original state. Let me play it again. It is very small micro switch, so, and even this displacement is very small with 2 actuators, but with 2 terminal electrical connection, it can switch back from one state to another state. This is the push on process, this is the push off process. Yeah. So, we have, let us go back to push on, from that state it will go to the other state, and when you do the other one, push off, that is the next one. When you do this, it again goes back to that state. Okay. This is also bimodal bistable, where we are looking at the arch. So, that we have the arch here. So, let me go back, get the pen. So, when we have this, second actuation is, let us say you apply the force here, it is going to switch to the other state. Now, second port, if you pull it like this also, it will switch back from there. So, this is the port 1 actuation, this is the port 2 actuation. The port 1 actuation also, it is like either you apply the force there, that is not what we have here. So, what we have is to switch back this one, or like this, switches and then goes back to the other one. So, here it is downwards to begin with, it is like this. When you apply the force like this way, it will go there and then push it this way or that way. There is a push off, it is already here. You go to push on 1, this has a slight slope. When you apply the force, it is going to switch here, push on and push off with the 2 terminal. So, we have macro and micro. There is a meso one, unfortunately I cannot talk about this, but there is this circuit breakers which can benefit a lot from these bistable switches. So, they have plenty of applications which we had discussed, and we will be discussing the easy chair design in much more detail in a later lecture. So, bistable phenomenon, again to summarize, it needs to have an elastic element that stores energy and stores energy to the maximum during the travel, and then it decreases. So, state energy should increase and then decrease. If that is the feature, it will have bistability. And decreasing state energy for a compliant mechanism is advantageous from the viewpoint of mechanical advantage also, as we had discussed earlier. So, bistable devices inherently have this non-linearity which we exploit and get this feature of having states with stable and another stable, in between they will be unstable. All these things that we have this feature. It is a very nice feature to have in a compliant mechanism when you want to switch between two states, and they have applications from aircraft wings all the way to simple hair clips, as we had discussed. Thank you.